Hello and welcome to the directions video for the light diffraction lab. In this lab, we're going to be using laser light, as you can see, a green laser to start with, to measure the width of a human hair. This is because the diffraction pattern gives away the hair width. Essentially, our hair is acting like a single slit, and the light is spreading out after passing through that slit. Of course, it's not, it's an obstruction, but it turns out that the effect is actually quite similar. So I've set it up here by poking a hole in a box and mounting the laser. That is actually holding down the power button on the laser as well, which is really convenient. You can also tape down your power button. And over here, I have taped a hair on to the outside of the box, so it's suspended across the opening that I cut open with a pair of scissors. All right, and this is a shoebox. Okay, so where does the laser light go? Well, on the wall across my garage, I have set down a black object. It doesn't have to be particularly large. You could also cover something with a black pillowcase, or just have something that's dark and not too glossy or reflective. And again, doesn't have to be perfect, but just that's going to be your backdrop. That's going to be your screen for the laser light. And in my case, it's about 9 feet away. It doesn't have to be that far, but that's just gonna allow me to get a really high quality image because I'm gonna have a nice distribution where, in other words, my pattern is gonna spread out over a big distance. Okay, so let's head on over there. Okay, there it is. Okay, so if we look here, I'm blocking the light, so I'll get out of the way. But there is our diffraction pattern. Now, I say it's a single slit diffraction pattern because it has one large central peak, all right? Now, it almost looks like that central peak is composed maybe of two pieces, but it actually is a single central peak, okay? And furthermore, we can see the other maxima to either side, okay? Now, it's always a case that, maybe with the naked eye, you can see things better than with the camera here. And of course, in the video, you're gonna get a much lower image with worse contrast than when you actually use the photo. So in other words, what you're seeing is gonna be worse than the photo I'm gonna take in order to do data analysis. And that's what I'm gonna do here. I'm gonna take a single photo, or maybe multiple ones so I can choose the best one. And then I'm gonna analyze one photo, one chosen photo, for this color laser. I'm gonna do this again for 2 other color lasers. And then the rest of the lab is going to be analyzing those photos, both for measuring distances and for measuring intensities using a program called ImageJ. And by the way, the distances are made possible because I have a scale in my photo. All you have to do is include a ruler that has centimeters, and then you can relate the pixels in the photo you take to the actual physical distances. Okay, all right, well, I'll come back in the second part of this video and talk about the analysis on the computer.
Okay, well, continuing with the lab directions for our light diffraction lab, let's talk about the analysis portion of the lab. Now, I want to be clear about what we're doing here because we're using a piece of software that I'm sure many of you have not used before called ImageJ. It's from NIH, so it's from a very reputable source, and it's open source. There has lots of different modifications, and we're going to be using some of its basic features. It's very easy to download. You can download it for any operating system, including having versions that are operating system agnostic. So lots of good options there of how to get it. So it should be no problem to run. And that's what I am running here today. So let's take a look at that. All right, so here's what the program looks like when it's running. It has this very low profile menu. And of course, there's a menu up top. Now, my version of ImageJ is called Fiji. That's just a compiled version that I have for my Mac. Fiji is an acronym that stands for Fiji is just ImageJ. Okay, so as you can see here. So we're going to go ahead and open our photo, all right? Because I have taken a photo of my distribution, my diffraction pattern, okay? So here it is, right? Here is my ruler, so we can scale up what a centimeter is, make that equivalent to pixels. My image could be a little bit straighter. The angle here isn't great because there is kind of a parallax effect, but it's good enough, so we'll certainly make it work. And hopefully that will average out since we'll be measuring things on both sides, which is one of the reasons I have you measure distances on both sides of the maximum, the central maximum, to get at any sort of actual bias between the sides due to the angled effect like I just mentioned. But here's the image. One thing I need to do is I need to convert this to a JPEG, for example, because it's not going to work in its current format, the HEIC format that an iPhone produces. So I'm just going to export it as a JPEG. All right, and I think I saved it to the same space. All right, so let's take a look. Looks like I did not. Okay, let's do that one more time. All right. And JPEG. Okay, so there we go. So now we can just simply go back to Fiji or ImageJ, and we're going to go ahead and open up that file, the JPEG that I just created. There we are. Okay, so it's opening it up. All right, now we're probably going to want to zoom in on this. Okay, so let's do that first. So to zoom, you simply will leave your cursor over the portion that you want to be the focus of your zoom, and then just do Command+. Okay, so if I wanted to zoom in this corner, I'd leave my mouse in that corner and it would zoom in towards that corner. But I'll continue zooming in towards the center. All right, now I need to resize this because it's not showing everything now, because as I zoomed in, I lost some of it. And I can scroll around to where I want to be. All right, so that looks like a good zoom. Now, one thing I'm going to be looking at, of course, is going to be the distance between these maxima. All right. Now, to be fair, we'll be looking at the distance between the maxima when we're actually looking at the plot of intensities, because that's what shows up, or the peaks. But when we actually measure the distances that we're going to use to make our calculations of width, of course, that formula, as is explained in the lab handout, is based on the distance from the center of the central maximum to the minimum. All right, and it's just a nature of how diffraction patterns work for single slit, which this is behaving like. And so that's why it makes sense, instead of measuring the distances between maxima. And really, it all comes down to the fact that the central maximum is twice as wide as any other maximum. That's a characteristic of single slit patterns that doesn't show up with double slit interference patterns. And because of that, it actually makes sense to measure the minimum, because they're symmetrically distributed about that central point, whereas these other points would all be 1.5 distances away. Still symmetric, but it would just be a little bit more complicated. So the more intuitive approach is to measure distances to minima. Okay, now I need to make my window a little bit bigger so I can include my ruler in there. There we go. Okay. All right, so the first thing I'm going to focus on is kind of the material in part 1 of the lab, which is measuring distances. Okay, so to measure a distance in ImageJ, we want to set the scale. Right, so you see that option under Analyze, and it says Set Scale. Now, before I'm going to set the scale, I'm going to go back to the window that has my commands. So I'll go over here. All right, let's find it. There it is. All right. And so this window has my commands, and I want to use the straight segment tool. This is actually the same tool that we're going to be using for the plot profile, but for now we're going to use it to measure distances. Okay, so I'm going to now zoom in on the ruler a bit more. Okay, because I want to get a real clear image of centimeters. Okay, so you look, of course, I'm hovering over the inches, but I care about the centimeters over here. So let's get one distance that is exactly 1 centimeter. All right, I zoomed in again. I'm going to draw a straight line. I'll draw along the edge to kind of control for any error there, from the 7 to the 8. Okay, so kind of within the scale of this photo, everything hopefully being planar, right? So no varying distances from the camera. That is 1 centimeter. Okay, so then I go back up to Analyze and Set Scale, and that distance shows up automatically because I use the line segment tool, and its distance shows up in pixels. All right, so that's exactly how many pixels long that line is that I just drew. Now I'm going to say that that is equivalent to 1, okay, and then centimeter. So I just changed the generic name. So look what it has there. Now the scale is that every 89.9889 pixels is 1 centimeter. That's global, right? Now it doesn't really matter because we're not doing like stacks of images or anything, but I'm just always in the habit of selecting that. Okay, so we can zoom back out, because now that we set our scale, look what we can do. We can measure distances. Now I'm just kind of zoomed in over here on the left side of the pattern, but let's go back to our tool, our line segment tool, and let's look at one of the distances we care about, the distance from the central maximum to the first minimum. And I will actually zoom in a bit more here. Now, you got to just choose the same point, like what is the center? There's some ways you can go about doing that by drawing a line across the width to begin with, okay, and then finding the midpoint, or you can just be consistent and always use the same one. Okay, so I'm going to go ahead and draw a line from the center of the central maximum to the first minimum. Okay, and try to keep it along a single axis, an axis that represents the pattern. Okay, so I think my issue is I started a little too low, so I'll start a bit higher. Let's try this one. There we go. It looks a little bit more reliable. All right, and there's obviously inherent human error in here. Okay, All right, but there's my distance. Now what I do is I say Control M. Now you can choose this from the menu as well, but this is a very helpful shortcut key. Just Control M, and that's going to give me my length. Okay, so it gave me some things that don't make sense, like its area, because this is not an enclosed space, but it always does that. It also gives a mean. It'll give the coordinates, because anywhere I mouse over this photo has pixel coordinates. But look what it gives me that is important, the length, all right? 2.804 centimeters, actually in centimeters. As long as I reliably had my ruler in the right place, that is the actual distance, okay? Now, I also know the actual measured distance, as you saw in the first part of the video, from my cardboard box that housed my laser and the suspended hair, the taped up hair, to the screen, which was just the piece of plastic, the stool. And so that distance I would have measured. I would measure it out, right? And in my case, I'd probably have to use my measuring tape and in inches, then convert it over to centimeters, because I don't have a long enough measuring tape in centimeters. But whatever case, you're gonna measure that total distance. So now with this value, this 2.804 centimeters, which is your Y value from the formula in the lab handout, and now you know your D value, the distance from your mounting to the screen. Well, there you go. You can start actually checking the calculations for the width of the hair. This would be the first example, the first calculation. And you're going to do that over and over again, a total of 8 times for this color, all right? So here, we'll go ahead and save the measurement. And notice also the angle is a meaningless value. That's just kind of measured in unit circles, starting from pointing in the positive X direction, or the right direction, and then going counterclockwise from there, which is why it's almost 180 degrees. All right, but anyway, all right, so that's it for distance. And again, you would do it over and over again. Okay, fine, I won't save this time. All right, and so we could then measure distance again, to the next minimum. So something like that. See? Okay. All right. And each of those would independently use to calculate the width of the hair. You're just getting repetitions, essentially, getting an average that becomes more reliable than a single measurement. All right. So now we're going to measure. We're going to zoom back out, because we're not going to measure anything so much as visualize. Okay. Now there's going to be a relationship here in terms of the distribution we get, but it's not an exact measurement. We're more interested in a trend. And of course, what I'm hinting at here is the intensity, because obviously the central peak is very bright. Okay, it's washed out inevitably right in the middle, and that has to do with some of the reflective qualities of the hair. I suppose we could spray paint it with matte black spray paint, and it would work better. But regardless, we've got this this central maximum, twice as wide as any of the other ones. But then the first order one over here, in terms of the first order maximum, well, that's going to correspond to it just has less intensity, all right? And then the next one is significantly less intense. You can see they become very dim quite quickly. And what I really like about this is you can just barely make out the fourth one on both sides. So it's dramatically less bright. So that means when you actually do the plot and analyze the grayscale values of all these pixels, we're going to get a really nice trend. Okay, I'm going to zoom in just to see if I can. Yeah, this seems like I can get all 4 this way, because I have 1, 2, 3. Nope, I'm missing the edges. Yeah, so I need to zoom out. All right. So yep, I'll just draw this carefully, because you see the 4th order one over there in terms of the maxima. Okay. All right. So let's draw our line again. So I'm just going to use, as I said before, the same line segment. It's just longer this time. Okay. So I'll start just past the 4th maximum on the left-hand side and draw it straight through all of them, kind of straight through the middle, until I get the 4th maximum on the right-hand side, which it just barely shows up. But it certainly should show up in the distribution. There's our line, right? Looks pretty reliable, especially considering the awkward tilt of the photo, the way I took it. All right, so now we go to Analyze, and we go to Plot Profile, right there, one of the options. Okay, just three down from Set Scale, the only other option that we use and we need to use in this lab. Okay, so Plot Profile, and there it is. There's our distribution, right? So we can clearly see this idea that the center is very bright. It's got that one washed out point, but we can kind of get an idea that the side, maybe, you could almost project this as a more reasonable curve, right? So maybe, get some idea. But ultimately, if the middle is washed out, you don't need to include it. But what you are going to do is you're going to look at values, and again, this is going to be somewhat subjective. Like here, I'd probably choose a peak value on the right hand first order maximum, or the one that's immediately adjacent to the central maximum, as a value of maybe 98. You can work around in here kind of what it is. Okay, so there's 110, but so you kind of just averaging it out, right? So probably somewhere in the 90 range. Down here, this is definitely going to be around 60. maybe 65. Okay, so in terms of the y value. All right, so let's get this. Yeah. And you can see it's actually, as I move the mouse over, it's tracing it, which is why it jumps around so much. So it's not showing me like so much the coordinate as it is showing me it's like, it's locking onto the curve, the values down here, okay? The values that you can see rapidly changing, okay? Which is actually very helpful, okay? But so there you go, you can find that value. And then when we get to the next one, that's gonna have a y value somewhere in the 50s, maybe 55. And then we get down to this one, which is, you know, obviously like around 45. And then we have something in the low 40s, so probably like 40, 42, okay? And it gets a bit messy over here, but we can still see, right? You know, something that we had, you know, a value around like the 60s, and you might be like, oh, but it's really asymmetric, and that's true. It is asymmetric, okay. And some of my previous photos weren't as dramatically asymmetric, okay. So you know, you could definitely, you know, try a different one. But the one thing that is interesting here is that despite that, we're interested in the ratio, right? So we care about how much it goes down, not so much the fact that this side is brighter and so all the grayscale values are higher on the right-hand side, but just that there's a functional relationship between the ratio of this height, for example, and the next one, the next higher order peak, and then the ratio of that higher order peak to the next one, because that's the only thing you're actually going to graph are those ratios, okay? Okay, all right, so let's move on and just briefly talk about kind of the last idea of creating a table, right? So you want to consider a table of your values where you have the calculated hair widths, you know, based on and that this would go back to the part one, the measurements, and then you have the standard deviations of those hair widths because they all come from, you know, 8 separate measurements, and then you can see, well, do they overlap? Right? You know, so if I got these 3 values as my measured hair widths, my 3 different colored lasers, laser 1, 2, and 3, well, you know, did I get the same number truly? Or I mean, or are they different? Because it's 130, 140, 122. Well, to tell if they're statistically, you know, all represent the same value with just some spread, we need to see if their standard deviations cross. And in this case, they do. And you could visually show that, although you don't have to show that their standard deviations kind of nicely overlap. And so that means that it is reasonable to say statistically that this is all the same value, and that the hair width is probably just the average of these 3. So 130 plus 140 plus 122, right? And then just to average it. And these are measured in microns. And then, of course, you're also going to use Excel to create the graph of the aforementioned ratios of intensities. Okay, well, I think that wraps up the summary of the lab, and hopefully gives you a good introduction to using ImageJ, which can, you know, do really cool things like this. You're going to include your plot distribution as well. So thank you so much for watching, and have fun at the lab.